Welcome back, Calculus. These are the video notes for linear approximations and differentials. So previously in calculus, we have talked about writing the equation of the tangent line at a given point, and we can create a formula similar to this one here that says y equals f of a, which is your y value, plus your slope, f prime of a, times x minus a, which is your x coordinate. And so this is a variation of point slope formula. And we know that the tangent line to a graph will always be equal to the function at the given value, because that's how we construct it. And this is what tangent means. It means to share exactly one point. And then we also know for x is really, really close to that tangent line, we're going to get approximately the same value on the tangent line that we do on the function itself. Those two values should be really similar. Think of a curve like this, and then your tangent line here, and they share this point. So all around here in this window, you've got values that are really close together. And so we can use the line to approximate the value of the function for x is really, really close to the tangent point. So here's our notation that we're going to be using. It's capital LX. And this is called the linearization or linear approximation or tangent line approximation of the function at x equals a. Now think about it like this. I realize now that we have technology and calculators, why not just plug in the square root of 9.1? But this technique originated before we had calculators that were able to quickly do these calculations for us. And this was a very, very convenient way. It was one of the purposes of calculus to evaluate unusual functions. So to find the linear approximation, we're going to do Lx equals f of a plus f prime of a times x minus a. And then in this example, a is going to be 9. And then eventually, x is going to be 9.1 when we're ready to evaluate. So let's start with the derivative. F prime of x is equal to 1 over 2 rad x. And so if we plug in 9, we get Lx equals f of 9, f of 9, which is the square root of 9, plus f prime of 9, which is 1 over 2 times the square root of 9, x minus 9. So this right here, this is our linear approximation. This is the first part of the question, find the linear approximation. Now we're just going to use it to evaluate 9.1. And we're going to get a pretty close answer without even needing the square root. 1 minus 9. And so we get 3 plus 1/6 times 0.1, which is 3. So 1/6 is 0.16 repeating. Add one more decimal to that. And so we've got an approximation of about 3.016. Compare that with the square root of 9.1 from your calculator, and you'll see that the two are actually very, very close together. So looking at the calculator, we get 3.01662, and our approximation is 3.016666666. So this is pretty close within the thousandths. Example 2, find the linear approximation f of x equals sine x at pi thirds. So we're going to do f of a plus f prime of a, x minus a. The derivative of sine is cosine here, and we just plug it all in. So Lx is equal to sine of pi thirds plus cosine of pi thirds. And this requires some trig unit circle knowledge here. X minus pi thirds. And that's going to give us, sine of pi thirds is 1/2 plus the square root of 3 over 2, x minus pi thirds. Now be careful here. So this is our linear approximation. That step is done. We also need to approximate 62 degrees, except that's a degrees, and we're going to need to convert that to radians. So radian conversion is pi over 180. And I know this because pi thirds was measured in radians. So L of 62 degrees is 1/2 plus radical 3 over 2 and 62 pi over 180 minus pi thirds. Go ahead and type this in, and then compare this answer to the actual value of sine of 62 using your calculator in degree modes. So 3/2, 62 pi over 180 minus pi thirds. We've got about 0.53. Making sure my calculator is in degree mode. The sine of 62 degrees is nowhere near that answer. Oh, let's back that up. This is an error. Sine of pi thirds is rad 3/2. Cosine is 1/2. So it helps if you actually take a minute to think about the unit circle instead of rushing forward. Let's fix that with our calculator, and hopefully we'll get an answer that's actually similar this time. Yeah, so we've got 0.8829 for the true value and 0.8834 for the approximate value. Much better. All right. Find the linear approximation of f of x equals 1 plus x to the n power at x equals 0. So that's our A. We're going to start with our derivative. You'll notice that this problem does have two variables, but that's okay. We're still going to approach it the way we would any other derivative, and we'll talk about how we can get around these two variables. Lx equals f of a plus f prime of a, and I highly recommend rewriting this formula each time. It'll help you commit it to memory. L of x equals, and so for this first one, we're going to be plugging in 0 for a, so let's just do a little side thought. F prime of a means plug in 0. And so we've got n times 1 plus 0 to the n minus 1 power. Well, 1 to the n minus any power is going to be 1. So this all simplifies to just n times 1. So we've got n here. X minus 0 is just x. And then f of a, if you plug in 0 right here, you've got 1 plus 0, which is 1. And 1 to any power is 1. So here's our linear approximation. It's actually quite simplified down. Now looking over here, if we compare this to our formula, we really got to think about it here. It's obvious to me that n is 3. And in order for these to be the same, x has to be 0.01. And this is a little less obvious. So for our Lx, we're going to do L of 0.01 equals 1 plus 3 times 0.01, which is 1.03. Compare that to the true value using your calculator. 1.01 to the third power is 1.0303. So very, very similar here. And so our two answers are the linear approximation here and the estimation using the approximation. So differentials are going to be in part 2 of the video notes. This is going to conclude our video notes for linear approximations and differentials. Thank you for watching.